right, let's go over your transforming and combining the random variables assignment and see how you did there. So first, we were asked to create that probability model. So remember, we want to know what perspective that we are doing this random variable from. And we were doing the perspective from the player's perspective, not the company's, not Miss McClellan's, not the casino's, okay? So that means that then, so here's how I wrote this. See, the player has to pay $2 to play, but then can win $5. And so then that's a net of $3 profit. Okay, that will happen if the player gets a 3 or a 5. So there's a 33 to 30% chance. So 1/3% chance that that'll happen. So a third of the time, the player's going to make $3. All right. But with the other, if anything else happens, then the casino dealer gives the player nothing in return, and so then they lost their money. So that's losing $2. The casino gives them back nothing, so they've lost their $2. That happens 2/3 of the time. All right. So what's going to happen overall in the long run on average? And so there we have it, $3 times a third plus negative $2 times 2/3, and that's how we get that. And then actually, I don't know why I have this plus dot 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 here in the middle, but it's 3 minus a negative 0.33 squared and a third. Negative 2 minus a negative 0.33, 2/3. Okay, so it's a $2.36 standard deviation. All right, so interpret. So if you play many times, then you're going to lose, on average, 33 cents per play. All right, so 33%. Now, as far as the variability goes, you could say 68% of the time you're going to be within this much and this much, or you might say 95% of the time, because that's not outliers. So you could think of it in terms of that. So I kind of thought, okay, what's 2 standard deviations up is $5.50. 2 standard deviations down is, or you could lose as much as 505 per play or win as much as 439 on average, okay? But overall, you are going to lose 33% on average. Now, look at how this works. We are now combining 3 different events. So what would you expect to happen on 3 different plays? So we expect that, we would have this happening on average on the first play, this happening on average on the second play, and this happening on average on the third play. So really, overall, if you're going to play 3 times, you're going to be losing about $1 on average in the long run. Okay, so, and then with what standard deviation? So remember that standard deviation, that diva has special rules all the time. So that standard deviation is going to be happening 3 times, not just 2. So not even the a squared plus the b squared. It's the standard deviation squared plus the next one's standard deviation squared plus the next one's standard deviation squared, and then we square root that. So that's that 4.09 as the variability happening amongst 3 plays. So let's expand upon this process in part D, and let's see what that would look like. So I'm already kind of thinking through this. See, easily I knew I had 3 of the negative 0.33s. So if I did 30 different turns, then I have 30 of the negative 0.33s. So if I'm going to be, every time I'm playing 30 times, then I'm going to be losing $9.90, okay, on average. Out of 30 plays, that's how much I'm going to be losing. Because see, when I played 1 play, it was negative 30, it was lose 33 cents. So when I'm playing 30 plays, then it's this. But with what standard deviation? So remember here in part D, where we had, this place squared plus this place standard deviation squared plus this. So we had 3 of the standard deviation squared. So I could have, and I didn't write this out this way because I didn't want to confuse you, but here you could have written this as 3, or the square root, of course, square root of 3 times 3 of the 2.36's squared. Okay, so that's really what we're doing, is the square root of 3 of the 2.36's squared. So that's then, if I expanded upon that to these 30 plays, then that's 30 of the 2.36's squared. And so this is actually going to kind of take us into what we end up learning in today's lesson, or kind of taking a look at today's assignment. But anyway, so that comes out to be a variability of $12.93. Okay, so let's take a look at this next one. So draw the normal model of what's happening for 30 plays. So we took this mean and standard deviation for from part E. And then here's how we did this. So I've got the mean is negative 90. And then I added 1293 up. And then I subtracted 1293 down. And I labeled this because I've got to keep this context of what's happening straight. So this is the expected profit for 30 plays of the game. All right. So then the question is this. So there's the normal model with the labels, okay? And then it says notate where the player breaks even, and that's your profit of 0. So that's this line that I have drawn here at about 0. So I approximated where I thought that was at 0. Okay. Compute the proportion of times that the player actually comes out ahead when playing 30 times. Okay, so say you go in each day and play 30 plays a day, then how many days are you going to come out ahead? So I had to then notate, okay, where is the ahead? Well, of course, that's to the right of this breaking even. So to the right, that is the part's greater than 0. So then I want to find out how much area I have shaded here in green. So I did a z-score. X is a break-even point of 0. X minus the mean of negative 9.90, divided by the standard deviation is 0.77. So that is the location of the z-score of 0 is 0.77 standard deviations above the mean. And then so I norm CDF'd from that 0.77 up to 99. So that tells me that 22.06% of the time the player comes out ahead when playing 30 times. And so I'm thinking right now, that's not a good deal. So to me, it almost seems like, I can clearly see the more you are playing, the more that mean is kind of scooting down and down and down and down. And then I bet that this green section, the more times that you are playing, then this green section is getting smaller and smaller and smaller and smaller. Okay? All right. Next. So here we had a local car dealership. The mean number of cars was 3.1. And let's see here. Let me move this out of the way. Okay, so the facts they gave me were that the mean cars is 3.1 with the standard deviation of 1.1. That's the cars sold in the week. And then they gave me the commission function for transforming. So we're going to transform from cars into commission money. So here we have that the dealership pays the $300 plus the $250 per car So you can see that that's $2.50 per car. So there's the function. All right, what is her expected total weekly pay? So see, that's my average. What is the expected? So then I'm going to use my function, 300 plus 250 times 3.1. And so she's expecting to make $1,075 per week on average. Keep in mind that this the mean does what you expect it to do and just plugs itself into the function. Addition, subtraction, multiplication, and addition apply. But with standard deviation is a diva. And you should remember that every time you are using standard deviation, you should stop and think, because when there's got to be some special rule happening. Okay, so remember, standard deviation always has special rules. Such a diva. Okay, and remember that addition is not changing the standard deviation, so no plus 300. So the variability in her pay is 275. All right. Is this a person? Oh, it is. She is selling. Okay. So now, after the salesperson has worked at the dealership for many, many weeks, what's the probability that she would average 1570 a week or more? So let's see. So I did a normal model. And of course, I have this average at 1075. And we want to know 1570 or more. See, so I'm going to be using my mean and standard deviation. X is 1570. So my z-score is x minus the mean over the standard deviation. So my x value is 1.8. And then to get that area above that, because they want to average that much or more, I'm going to norm CDF. So if this person, if she's wanting to be able to budget or think, ooh, I want to buy a new house, but if I do, I need to make 1570 per week or more. Is it going to be happening? And I'm going to say to her, honey, you better reevaluate, because no, that's only going to be happening about 3.59% of the weeks. Are you going to make that goal? Okay, so let's get realistic here. All right, next. Amazon, you know what? This is so true. This actually is that. I mean, I cannot tell you how much all the places that statistics is happening. They do this in here. They employ traffic engineers when computing the best delivery routes. Such a huge operation. I mean, even things that detailed go into this whole program. But anyway, so they study traffic patterns of two busy intersections. So they're trying to figure out these things going on. So anyway, they know the intersection and the number of cars that are waiting to turn left. And then at intersection D, the number of cars waiting to turn left. Because you know what? I'm going to tell you this right now. They already plan routes for delivery drivers on the way that the drivers go is the ones where they take the most right-hand turns. Why do they take the most right-hand turns? Because right, they can turn without having to wait red, but left, they're going to have to wait. So that's why they're investigating this. Okay. At Street D intersection, the average number of cars waiting to turn left is 25 with a standard deviation of 7. Okay, so here we go. The traffic engineers want to find the expected number of cars turning left at the intersections combined. So maybe the route is having both of those situations. They want to see what they're dealing with here. So we've got that 17, so that just combines 17 plus 25. But standard deviation, Pythagorean theorem of statistics, 4 squared plus 7 squared, and square rooting it. Now, let's do this. So we set this normal model up with a mean of 42. And we want to know what's the probability that the combined cars of the two intersections averages 30 or less. So then that's my x value of 30 or less. So I'm going to do my x minus the mean over the standard deviation. I have a negative 1.49, and I'm going to norm CDF from negative infinity up to that point. So only about 6.81% of the time will those intersections average 30 cars or less. combined. Okay, moving on. Here we go. The next one. Ooh, this one is so interesting. Okay, so first, here we go. We are talking about the viscosity of liquids. So, of course, that is having to do with the thickness of the liquid, okay? How much it's sticking to the sides, all that kind of stuff. So they do these measurements and they're determining its viscosity based on the length of time that it takes to run through a particular tube. Okay? So two different motor types are compared. Motor type Q. So here I summed it up here. Q's average and Q's standard deviation. W's average is 14 seconds and standard deviation of 3 seconds. Okay, so find the expected value for the difference between those lengths. Now, you have an option. How do you want to subtract? You can do Q minus W or W minus Q. It does not matter. Your numbers might vary a little bit in the interim. For example, if I did W minus Q, I just chose W as the first one because it's the larger number and I like to deal with positives. So that's personally what I thought about why I wanted to do W minus Q. And so that was 4 seconds. But if you did Q minus W, because that's how it was written, then you have a -4 right here. Now, FYI, regardless, you have the same standard deviation, whether you did W minus Q or Q minus Q minus W. The standard deviations added, even though you're finding the difference between them. All right. So now let's do this. This is important. So here we have the normal model for the difference in their times. So on average, it's 4 seconds. If you had done the other subtraction, you actually will have what I'm showing you, but the mirror image to it. I mean, you would actually have the -4 as the center, and then everything else is also flip-flopped as far as which side you show W and Q is bigger. Okay. So in the end, so if you did yours as Q minus W, you actually have the mirror image of this. Your blue area is, that top part instead of the lower part. But ultimately, the answer is still 13.35% if you did it correctly, even if you did Q minus W. And I think what I'll do is redo this problem and show you it. I may do another video, show you how you would do this page if you did Q minus W. All right, I may get to that. Maybe I'll do that one tomorrow or something. But here we go. All right, W minus Q is the way I subtracted. So you better label that you did W minus Q. So it says, notate the location where the viscosity of the two liquids is equal. So that is where the difference is 0. So that's this blue line right here. Okay. So there's that. Okay. So then part D. Label the side of the curve where Q is slower, takes more time than W. Okay. So Q is greater than W, takes more time. Q is W. Okay, so let's see. W, okay. So W minus Q. So W minus Q is greater than 0 over here, which means W is a bigger value, which means W, I had to write, my brain, it takes me a long time to get this. So I had to kind of write out all these synonyms. So W minus Q is greater than 0, which means W is bigger. Okay, I get that. Well, what does that mean? So that means W takes more time. W takes more time. So that means W is slower. That's why W is slower. And if W is slower, Q is faster. Okay? All right, then I did the reverse of that. Over here, W minus Q is negative. That means W is smaller. Or you could say Q is bigger, whatever. W is smaller means it takes less time to go through the tube. So it's faster, it takes less time. Okay, so I need to write that. W takes less time. Okay, so there's that. So Q is slower. All right, once I define that, then I go to the question, and the question says, compute the proportion of times that Q takes longer. So here it is. Q is slower. That means Q takes longer. So then once I've defined like what's happening on each side, then I go see what side does it want. It wants this side here. So I then find the z-score at the location by doing x minus the mean over the standard deviation. It's negative 1.11. And then I norm CDF from negative infinity up to that negative 1.11. Now, if you did the other thing, you got a positive 1.11 as your z-score, and you did from 1.11 up to infinity. Okay? So there we go. 13.35% of the time, it will take Q longer to run through the tube than W. All right, so that's a big one. All right, so make sure that you're doing okay on that, and really think about that problem if you struggled with it. Really kind of go back and study that particular problem right there. Okay, hope you did well on that, and good luck on today's assignment.